In this video, we're going to look at another example of infinite series. The question here is to show that the series summation k goes from 1 to infinity, 1 over root k, diverges to infinity. Let's start by writing the nth partial sum. Sn is equal to summation k equals 1 to n, 1 over root k, that's the kth term. This is equal to 1 over root 1 plus 1 over root 2, plugging k equals 2, plus 1 over root 3, plus ... and the last term, the nth term, is 1 over root n. Now the nth term of this series is f of n is equal to a sub n is equal to 1 divided by root n. Let's consider the related function f of x, where x is any real number. F of x is equal to 1 divided by root x. On the interval x between n plus 1, x less than or equal to n plus 1, and larger or equal to 1. Now take a look at the graph of y equals 1 over root x. You will notice that each of these rectangles, the area of each of these rectangles is actually one of these terms. The first rectangle has an area of 1 divided by root 1. The second rectangle has an area of 1 divided by root 2, and so on. So that's how we're going to go about proving that this series diverges, by comparing this to an integral, comparing the nth partial sum to a definite integral, and evaluating the integral. All right, let's do that. So we have Sn is equal to k equals 1 to n, 1 divided by root k. This is equal to 1 over root 1 plus 1 over root 2 plus 1 over root 3 plus ... 1 over root n. This is equal to the sum of the areas of the rectangles A1 plus A2 plus ... the last rectangle AN. Now A1 is the area of the first rectangle, so that's equal to f of 1 times 1, the height of the first rectangle times the width, which is 1. And the height is determined by the function 1 over root x, so that's 1 over root 1 times 1 is equal to 1. Now the area of the second rectangle is equal to A2, is f of 2 times 1, and f of 2 is just 1 over root 2. That's the function 1 over root x times 1. That gives us 1 over root 2. Similarly, A3, the area of the third rectangle, is f of 3 times 1. This is equal to 1 divided by root 3 times 1 is equal to 1 divided by root 3. This is the area of the third rectangle. We're basically computing these areas. So we computed, this is A1 basically, the area of the first rectangle. We computed A2, the area of the second rectangle, A3, and so on. And now in general, AN, the area of the nth rectangle, is f of n, that's the height of the nth rectangle, times the width, and f of x is 1 over root x, so f of n is 1 over root n times 1, it just gives us 1 over root n. Now notice something, that the sum of the areas of these rectangles actually equals the nth partial sum for the series that we have, plus an is equal to 1 plus 1 over root 2 plus 1 over root 3 plus ... 1 over root n. This is equal to Sn. And since the areas of each of these rectangles, is larger larger than the areas under the curve of the function y equals 1 over root x, under the curve y is equal to 1 divided by root x. Let's go back to the diagram. You can see the area of one of these rectangles, of all of these rectangles, is bigger than the area under the curve. So A2, the area of the second rectangle, is bigger than the area under the curve, and so on for all of these rectangles. And for this reason, the nth partial sum, Sn, is larger or equal to the sum of these n rectangles, is larger than a definite integral, is larger than the area under the curve of the function 1 over root x. So integral from 1 to n plus 1, 1 divided by root x dx. This is equal to integral 1 to n plus 1, reverse the power rule. Let's rewrite 1 over root x as x to the negative 1/2, and reverse the power rule. Add 1 to the exponent, divide by the same. So we get x to the negative 1/2 plus 1, x to the 1/2, divided by 1/2, that's the same as multiplying by 2, evaluated from 1 to n plus 1. All right, so we have Sn is larger or equal to integral 1 to n plus 1, 1 over root x dx, is equal to 2 root x, evaluated from 1 to n plus 1, apply the fundamental theorem of calculus, and we get 2 root n plus 1, putting the upper limit in, substituting in, minus plugging in the lower limit, 2 root 1, that's just 2. Now, let's take the limit as n goes to infinity of Sn. This gives us the limit as n goes to infinity of 2 root n plus 1 minus 2. Clearly, this limit goes to infinity because 2 root n plus 1 grows to infinity as n goes to infinity. So what we have shown is the limit of Sn as n goes to infinity is equal to infinity. And we can conclude that the infinite series k goes from 1 to infinity, 1 divided by root k, diverges to infinity. Now let's look at a theorem. If the infinite series summation an, n goes from 1 to infinity, is convergent, then the limit as n goes to infinity of the nth term has to be 0. This is kind of easy to prove, so we may as well do that. Let's do the proof. Let's look at the nth partial sum, Sn. This is equal to a1, the sum of the first n terms, a1 plus a2 plus a3 plus dot 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 plus an minus 1, 1 before the last term, plus an. Now let's look at Sn minus 1, the sum of the first n minus 1 terms. We get a1 plus a2 plus a3 plus dot 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 plus an minus 1. If we subtract these, what do we get? Sn minus Sn minus 1. We simply get, well, if we subtract these, a1 is going to cancel, a1 minus a1, a2 cancels, all of these cancels, an minus 1 will also cancel with this term, so the only thing that's left is the last term of the first series, which is an. This is equal to an. So we have Sn, we've shown that Sn minus 1, Sn minus 1, the nth partial sum minus the n minus 1th partial sum. That difference is an, which is the general term an. And since we know already that summation an, n goes from 1 to infinity, converges, that is given in our theorem, that this converges, then the sequence of partial sums, the sequence of partial sums Sn also converges. Now let's assume that the limit as n approaches infinity of the nth partial sum is equal to s. Now we know that when n goes to infinity, n minus 1 also approaches infinity. That means the limit as n approaches infinity of the sum of the first n minus 1 term, the n minus 1th partial sum, Sn minus 1, is also equal to s. So we can show that the limit of an as n goes to infinity is equal to limit as n goes to infinity of Sn minus Sn minus 1. Distribute the limit, we get limit of Sn as n goes to infinity minus the limit as n goes to infinity of Sn minus 1. This gives us, what is the limit of Sn as n goes to infinity? Well, we showed that, that's just s. This is a convergent series, so it converges to a finite sum. And Sn minus 1 also converges to the same sum, s. S minus s gives us 0. So we have proven that if summation an, n goes from 1 to infinity, is convergent, if this infinite series is convergent, then the limit as n goes to infinity of an is equal to 0. All right. Now notice the converse of this theorem is not generally true, because earlier we proved that summation 1 over root n as n goes from 1 to infinity diverges to infinity, while the limit of the nth term, limit as n goes to infinity of an is equal to limit as n goes to infinity of 1 over root n, the limit of the nth term is 0. So the converse of this theorem is not generally true. That brings us to the divergence test. The divergence test states that if the limit of the nth term is not 0, or if the limit of the nth term does not exist, then the series summation n goes from 1 to infinity an is divergent. We're going to use this theorem to essentially to do this example. So we have showed a series summation n goes from 1 to infinity log of 2n divided by n plus 1 diverges. Let's take the limit as n goes to infinity of log of 2n divided by n plus 1. Bring the limit inside the bracket, so we get log of the limit as n goes to infinity of 2n divided by n plus 1, divide by the highest power and take the limit as n goes to infinity, we get log of 2. The limit of the nth term is log 2, is not equal to 0. So we have shown that the limit as n goes to infinity of the nth term is equal to log 2, and that's not equal to 0. Well, the divergence test makes sense intuitively, because what we're saying is at infinity, we're adding terms that are not approaching 0, so the total summation has no chance of converging to a finite sum. So in any case, this series diverges. This series diverges by the divergence test. So this is the first test we often use because it's easiest to do just to rule out whether it converges or diverges. Just look at the nth term. If the limit is not 0, then we know for a fact that this series diverges. But this is very important. If the limit is equal to 0, that doesn't tell us anything. We have to do some other tests that we're going to be looking at later on in the course. So this series diverges by the divergence test. So key concept, if the limit is not zero, the limit of the nth term is not zero, the series diverges for a fact. But if the limit of the nth term is zero, it doesn't tell us anything. And we looked at an example. Here we have summation 1 over root n. This series diverges to infinity while the limit of the nth term is zero. So it's only when the limit of the nth term is not zero that in that circumstance we can make a conclusion that the infinite series diverges. But if the limit is zero, it doesn't tell us anything. If the limit of the nth term is zero, we have to do some other test, and we'll be looking at those in a later videos. All right, thanks.